for the brief introduction. So, to be honest, I'm also not quite sure how one pronounces the two names. So there are two Belgian mathematicians or actuarial scientists. I have never met them personally, so I'm not quite sure how to pronounce them. But Goovaerts, I think, and Vylder. So yeah, so it's a topic from actuarial sciences. So it's the conjecture is a conjecture about a modification of the classical model from ruin theory, and this is how I want to start this talk. I briefly want to recall this classical model. I mean, it's a finance seminar, so the topic is more from actuarial sciences, but of course the two fields are intersecting. And in the end, in ruin theory, one is interested in some ruin probability, but that's of course the same as a default probability in some sense, which is also a main main object of interest in finance. So I think or I hope at least that you find this topic interesting. Okay, so let me briefly recall the some basic elements from ruin theory. So it's just a brief summary of what ruin theory is. So it's part of actuarial science. The aim is to quantify the vulnerability of insurers with respect to the vulnerability to ruin or insolvency. And the classical model goes back to Cramer, and Lundberg has republished the results of Cramer and further developed these results. So now let me recall this classical model. This classical model that is also called the Cramer-Lundberg model. So one assumption is that claims arrive according to a Poisson process. So the Poisson process kind of counts the incoming claims incoming to an insurance company. So these claims are the claims that the insurance company has to come up for, or to put it differently, to claims for which the insurance company has to pay. So we assume that they are coming in at according to a Poisson process with intensity lambda. So that's the first ingredient of the model. The second ingredient is the model of the claim sizes. So it is assumed that the claims are IID. So we denote them by x1, x2, x3. So x1 is the claim size of the first claim, x2 the claim size of the second claim, and so on. U is the initial reserve with which the insurance company is endowed. And finally, we assume that there are premium payments that are continuously coming in at a rate C. So the premium paid between time 0 and time little t amount to C times t. Now all these ingredients determine the so-called risk reserve process. So capital R stands for a risk reserve process, and the risk reserve process at time 0 is of course the initial reserve, and at any time t greater than 0, it's the initial reserve plus the sum of the accumulation of premia minus the claims that the insurer has to pay for. So there are two random components. First, the number of claims is random; it's NT, and the claim sizes themselves are random. Now, the crucial object of interest in this ruin model or in ruin theory is the so-called ruin probability. And this is nothing else but the probability for the risk reserve process to hit 0. So we see here two realizations of the risk reserve process. So here in the first realization, the process stays always above above 0 until capital T. So there is no ruin before capital T, and in this scenario, the process hits 0 here. So we have a ruin before capital T. Okay, here again, it's an overview of some of the objects. So the ruin probability is very often denoted by psi, and it's as a function of the initial reserve. or it's also often considered as a function of the initial reserve, and as that denoted by psi of u. And sometimes one is interested in the ruin up to some finite time horizon capital T, and then we write psi of u comma capital T. And these are the objects, the main objects of interest in this classical ruin theory. And surprisingly, there are only closed form formulas for a little special, for few cases, only for some special cases. And in general, one needs to fall back on numerical methods for approximating these probabilities. And there is a whole bunch of methods that have been used for approximating these probabilities. I mean, there are whole books just on approximation methods for these ruin probabilities. So one very nice example is the book by Asmussen and Albrecher. It's called Ruin Probabilities, and there they give an excellent overview on various methods. And so it's a mixture about, of course, you have also some analytical tools to get some approximations or asymptotic approximations. And one approximation method is based on a diffusion approximation of the risk reserve processes. So these risk reserve processes are jump processes. Whenever a claim arrives, you have a jump, a downward jump. And but it's possible to kind of scale the process in such a way that you obtain as a limit a continuous diffusion, or in this case, it will be a Brownian motion or a Brownian motion with drift. And for Brownian motion with or without drift, we have explicit formulas for the hitting time at hand, and we can take these hitting time, or I mean the probability for the, so we have a formula for the probability that a diffusion or a Brownian motion with drift hits a certain level. And so we can take these hitting time probability or hitting probabilities as approximations of the ruin probabilities within the Kramer-Lundberg model. And this works surprisingly well. So this is nicely demonstrated also in the book by Asmussen and Albrecher. Okay, so what will be my focus today? So today I want to speak about a conjecture that has been raised by the Vylder and Goovaerts. It's a conjecture that has been raised in a paper from 2000. So here in the first two lines, you can see the precise reference. So what de Vylder and Goovaerts have studied is the following modified risk reserve process. So we have still the initial reserves U, we have incoming premium at rates T, but now we look at some equalized claim sizes. So at time T, we look into the future up to time capital T. We take the sum of all claims up to time capital T and then average with n capital T. So with the number of claims up to time capital T. So the red part gives us the average claim size until time capital T. And now we multiply this with nt, with the number of claims actually until time little t. So I think this is best visualized, or this is explained with a picture. So here the blue line depicts the original risk reserve premium. You see you have a big claim here, then also a big claim here, a little bit. Then we have a tiny claim here and some a medium-sized claim here. Now the yellow curve is the modified equation, and you observe here we always have the same jump size. So jumps occur at the same time, but the jump size is always the same, and the jump size is the average of the jumps of that the original process, or the blue process, makes. And now the what de Vylder and Goovaerts looked at is that the ruin probability for this modified process, so this modified risk reserve process, so with which probability does the modified reserve process hit zero up to time capital T? And they formulated the conjecture that the ruin probability is smaller than the ruin probability in the original model, in the unmodified model. And this conjecture is still not proved, so it's still an open problem. And so far as I know from people in actuarial sciences, so many people have tried to prove this conjecture, but so far nobody has managed. And yeah, so maybe so why is it not obvious? So first of all, two things can happen. By equalizing, you can have a ruin for the modified process, but not for the original process. So this is this scenario. So in this scenario, the blue curve does not hit zero before capital T. So we have two small jumps at the beginning and a big jump in the end, but a strong positive trend. And this entails, or yeah, at least in this short period here. And but since we by averaging, we have also bigger jumps in the beginning, and this entails that we hit zero when modifying the process. Now, the other way is also possible, that by equalizing, you don't hit where you hit if you don't equalize. Yeah, so the blue curve is the non-modified process, and we have a very big claim at the beginning, which entails that the insurance company is ruined. But by averaging, the risk reserve process does not hit zero. So a priori, it's not clear. Or to put it differently, there are scenarios where averaging entails that no ruin occurs, where ruin occurred before, and there are scenarios where it's exactly the opposite. So pathwise, it's not clear or both. So the pathwise is not clear in which direction the relation holds, and yeah, that makes it quite complicated. Another thing that makes the analysis a little bit complicated is that the modified risk reserve process is not adapted to the standard information flow of the insurer. So in order to define R tilde T, you need to know the number of claims up to time capital T, and also the claim sizes of all claims until time capital T. So this is a process that looks into the future, if you want. Okay. So here you can see the conjecture again. So psi for any initial reserve and for any time horizon T, the conjecture goes that the ruin probability for the modified model is smaller than the ruin probability under the original model. So here are some results of that are known with respect to this conjecture. So for example, you can introduce some conditional ruin probability, but the ruin probability condition to the number of claims until time capital T. So this is denoted here by psi n. And the Vylder and Goovaerts have shown themselves that for n equal to 0, 1, and 2, the claim holds true. And also if you have an initial reserve of 0. And then there has been a contribution by Lefebvre and Picard showing that R tilde is smaller than or equal to RT in the convex order sense. And then there is a result by Christian Robert showing that if you integrate with respect to the initial reserves, so the averages with respect to the initial reserves also satisfy the relation. But the original problem is still unsolved. So what's our idea? So what do we do in the paper? Okay, so I completely forgot to speak about my collaborators at the beginning. So let me now do this. So all right. So the question, or I got to know this this conjecture when I visited University of Lyon in 2018. And there I've met Christophe Blanchet-Scali and Nabil Kazitani. Nabil Kazitani is working at an insurance and finance institute in Lyon. So it's quite a big institute there. It's called ISFA. And in some discussions, he mentioned this this problem, and then we started looking at this problem. And well, he also told me that quite a lot of people have tried to solve this, and I got a little bit said, okay, but maybe it's extremely hard, and um, could be also some waste of time. No, not waste of time, but you know, we can put a lot of time into this question and come out with no result. And then we in the discussions we had the idea to look at some modified or to slightly modify the question and to look at the diffusion limits of the risk processes and to check the conjecture in the diffusion limits. And okay, so the diffusion limit for the original process, this is known. So you get some Brownian motion with or without drift, depending on the model assumptions. But what is the diffusion limit of this modified process R tilde? So this was the first question, and we determined the diffusion limit, and it turns out that for these diffusion limits, we can explicitly, or we have explicit formulas for the hitting times, or the hitting probabilities, and by comparing the hitting time probabilities, we can confirm the conjecture within the diffusion limit. Okay, so let's let me now continue with diffusion limits of these risk reserve processes. Actually, what one looks at is the reserve process without the initial reserve, and usually also with the opposite order. So you look at the claims minus the premium, and that gives you the claim surplus process. And now, if you want to study the diffusion limits, you need to distinguish two cases. First case where there is no safety loading, and the case where there is a safety loading. So what is a safety loading? So usually the premium will be larger than the expected damage that you expect. So what you impose is, so what you would need to impose to have the same expectation is this C here. It's the expectation of a single claim times lambda. Lambda is the intensity of the Poisson process that models the number of claims. And so you would have to choose C if in expectation you don't make any gain. So if the insurer doesn't make any gain. And so this is the no safety loading case. So let's discuss this case first. In this case, one can show that, well, you scale time by n, and if you scale a space by 1 divided by square root of m, then you obtain as a limit some Brownian motion. So this is also best illustrated with a picture. So I'm jump one slide ahead. So here we see a surplus process. So if you want a minus or a risk reserve process with a, I don't know what the jumps are. This is the jumps are downwards. So this is also the risk reserve process. So it's minus the claim surplus process. Okay, so this is the original process. Now we scale time by m, which means time runs 10 times as fast as originally. At the same time, we scale space with 1 divided by square root of n. And then this we obtain a picture that looks like this figure here. And now we do the same with 50, with m equal to 50. And here in the picture at the bottom right, we do this with m equal to 200. And you see the curve looks almost like a Brownian motion. And this is what can be indeed shown rigorously. And here you can find the rigorous statement. So so at this point, actually, I wanted to briefly explain this. So I will turn on my electronic whiteboard. So check this. Okay. So we are in the case. So I don't know how this works now. I'm sharing. Hello, can you still hear me? I can't see.
Yes,
yes,
we can
yeah,
still hear you, but
you can hear me.
You're still in the slide screen, so we can't see your handwriting.
Okay. By the way, but you can't see me, my face. Can you?
No,
Is
we
it not
can't.
possible? Is it not possible to do the same?
I think if you have two devices, then you can log in with the same account, and then you can unshare, and we can see your face, and the other see the slides.
Okay. So I've got only one computer now. So sorry for this. But I'm just wondering. So I would have to stop sharing and the PDF, and then do share the. Maybe I share just the whole screen, so I need to.
Yeah, I think if you share the whole screen, maybe it's
okay. So let me do this. Thanks for the. So desktop. Doesn't allow me to share the whole screen. 1 second, please. He allows me to share OneNote. So that's strange. I don't know why. Okay, so then I will just share OneNote then. Okay, so we have. So this is the surplus process scaled by M. And so I hope you can read this.
We can read it.
Yeah, thank you very much for the feedback. So this is the claim surplus, and so we have CTM here. Now, what we are assuming, we are considering the case where C is equal to lambda times expectation of xi, so it's the no safety loading case. Now, what you do in order to prove this result, so you split up this term into two components, actually in three, but I will be roughly one can also do it with two. So we subtract here the expectation from the claims or claim sizes, and then we get as a second term expectation of xi I. So the so in C, so I replace C with lambda times expectation of xi I. So we have here a square root of m. Then we have ntm minus lambda tm. So this here is known to converge to a Brownian motion scaled by a lambda expectation of xi I. And one can show that this here also converges in distribution to some Brownian motions scaled by lambda variance of xi I. So if you think of if the sum is deterministic, so the upper limit of the sum is deterministic, then this is just the central limit theorem. So you need to be a little careful here because the sum is the number of summons is also random. So you need to be a little bit careful here, but you can indeed show that this converges also to some Brownian motion. So we have a Brownian motion here and a Brownian motion there, and they are independent. And then from the sum of these scaled Brownian motions, you can derive the limiting diffusion of the usual surplus process. Yeah. Now, what changes if you have surplus process. So let me write this in red color. So then we have here, okay, I need to delete this too. So we have here n capital T and now n little t divided by n capital T. We can do the same splitting. So the second term actually remains the same. The first term changes, of course. So maybe I will write the equality sign a little bit more to the left. Then we have here ntm divided by n capital Tm. Then we have here 1 divided by square root of m. And now here we have to sum up to time n. Sorry, I should have written this in red. Excuse me. So this is all modified. Tm. So here also Tm, Tm, Tm. Let me check. Yeah, this is okay. Now this here converges to T, and this here converges to some Brownian motion at time capital T. Yeah, and from that one can then obtain or explicitly describe the limiting diffusion dynamics. Okay, so now we'll jump back to the PDF. Sorry. Okay, so I hope now you can see the PDF again.
Yes, yeah, we can see the PDF. Thank you.
Thank you very much for this for the confirmation. Okay, so this here is the classical result. So if we scale the risk reserve process, then we obtain Brownian motion. This is the picture that illustrates this, and this is the theoretical result that describes the limiting diffusion if you scale the modified risk reserve process, or the modified surplus process. So here we don't have the initial reserve, and we have a minus, if you want. So we look at the claims minus the premium. Yeah, you see it's also an anticipating process. So we have a Brownian motion B, but the Brownian motion appears here at the time capital T. So this is some anticipating process, and it looks similar to Brownian bridge, but it's not Brownian bridge, but it's very similar. And if you see, if you take the value little t equal to capital T, then you obtain gamma times the Brownian motion T. So you obtain the same Brownian motion, or the same distribution of that you have at time capital T of the diffusion of the classical model variant. That's the diffusion limit in this modified equation, and now we can take this in order to compute the ruin probability. So here is a little overview again. So this is so the first line we can see the risk reserve process of the classical model, and the diffusion limit is the initial reserve minus a scaled Brownian motion. And in the second line, you see the modified risk reserve process, and the diffusion limit is what takes this form here, where B is again a Brownian motion. Now, at time capital T, these two processes coincide. You can so if you take capital T here, we have a 1. The sigma terms cancel out, and we have indeed equality. It's the same as for the initial reserve risk reserve processes. And now comes but we know more. So given that they all end in the same random variable, so if we can now look at the processes conditioned on the terminal value. if you condition a Brownian motion on the terminal value, or at the value at its value at time t, we obtain a Brownian bridge. And the same holds true for the second process. The second process will also turn out to be a Brownian bridge if you condition on the value of the process at time capital T. But the big difference is that the first Brownian bridge will be a Brownian bridge with diffusion rate gamma, whereas the second Brownian bridge will be a Brownian bridge with diffusion rate sigma, and sigma is smaller than gamma. So we have two Brownian bridges as diffusion limits, or as conditional diffusion limits, but the one has a larger diffusion rate. And the process with the larger diffusion rate will hit zero with a larger probability. And that means the conjecture holds true within the diffusion limit. So there is an explicit formula for these for the probability for a Brownian bridge to hit zero. It's a very simple formula, but I mean, you can. It's not written here on the slide, but it's written in the paper, and yeah, but you can directly read from the explicit formulas for the hitting probabilities of Brownian bridges that the diffusion limit of the modified process hits zero with a smaller probability than the diffusion approximation of the original process. So in other words, to put it differently, the conjecture of the Vylder and Goovaerts holds true in the diffusion limit. So that's what I wanted to present today. So here you can see the reference. It's this paper with Christophe and Nabil. So it has appeared already. It's published already. Let me stress that here for the talk, I just looked at the classical model version, but indeed you can generalize the model slightly. You can look at cases where NT is a general counting process and the results still hold true. And what is also possible to do is to look at the half traffic approximation of the risk reserve processes. That's where you so here I present the limit when there's no safety loading, but usually you have a safety loading. So what do you do then? So what you do then is you take the safety loading as an approximation parameter. You let the safety loading converge to zero, and at the same time you scale time with 1 divided by the safety loading and space with the safety loading. And then you obtain, in the classical case, you obtain a Brownian motion with drift. Yeah, and in the modified equation, you obtain again some analytically tractable process, and again you can confirm the conjecture within the diffusion limits. So I'm already at the end, but I mean, I very much appreciate that you give me that you would give me a whole hour. But so I think I don't need the full hour to make the point here. Already, I very much appreciate that you give me more time than people have in a TED talk, which is usually 12 minutes. So now it's 36. So you gave me 3 times the time that TED talk speakers have. So thank you very much for this.
All right. Thank you.